everyone. I'm Alex Armengol. I'm a postdoc in the T1 group. And yeah, I'm going to present part of the results that we have obtained so far. So to start, one of the long-term visions of our group is to be able to design smart augmented reality glasses, such as this one that can maybe help a maintenance worker to perform a maintenance task of a complex machine. So basically, the worker could ask, "Okay, help me to disassemble this complex machine in little by little steps," and then basically the smart AR agent would help in that. So this for that we need to design like small fundamental pieces. Like the AR has to be aware of the 3D space. It has to know which are the decisions to make in that space. It has to be able to guide with spatial holograms in that space. And also it's important to track the biosignals in order to know what's the stress level of the person, the tension, and the fatigue. And with that, basically the AR headset would go through little steps in order for the maintenance worker to succeed in the task. So I'm going to jump into the first part of the results that we've obtained so far in the fundamental piece of monitoring the cognition or expertise of the worker or any user. So we believe it's very important to be able to extract implicit human expertise. So the goal of this was to be able to monitor different variables at play while the expert is performing a task. And we showed that we are able to extract expertise by instrumenting their experts with sensors and the trainees and the tools that they use. And we show in a bit that we're able to extract some differences between experts and novices. And the other important result that we showed is that we actually believe that it's very important to be able to track the attention of experts when they perform a specific task. And we are able to show this attention in the form of heat maps in the augmented reality context using the AR glasses. So jumping into the first part of the results, we wanted to test this kind of technology in a context where it's important to, where there's a huge implicit knowledge component, and we believe that glass blowing is a perfect example for that. So, because usually teachers or experts usually find it hard to convey their knowledge to novices. So what we did is we instrumented the hot shop with different sensors. We put sensors in the pipe on the expert themselves using eye tracking glasses, muscle sensors, and so on. And one of the first results that we show is that we can basically create instructional videos like this one, where it's very easy for a novice to absorb all this information visually, like all the variables at play, like the rotation speed of the pipe, the orientation, where's the attention at each single time of the expert. So the red little circle is where the gaze is at. And with that, we see that it's very important. It will be very useful for novices to know what's how to perform these tasks from a point of view of the expert. And then when we analyze the data, we also show that we can quantify their expertise, and we find some key differences between experts and novices when we analyze the data. So in a way, we transform their implicit knowledge into a more explicit manner, and we believe this is going to be very useful for novices to receive from more informed or more quantified feedback. And then on the other piece of results, in here we show how we can track the gaze of users when they explore or they perform a simple task on a real physical object using augmented reality glasses. So we can track their eye gaze, and we can know where's the areas of the piece that receive more attention when they perform the task. So, for example, in these little videos, you can see on the top the red dot. That's exactly where the gaze is hitting the physical object, and then on the bottom you can see a report of where the attention was in the form of heat maps. And we think that this can be very helpful for learners to know where's the attention at every single point of time of experts when they realize the task. So there's a little demo outside. I encourage you to come check it out, and you can experience how useful it can be to visualize heat maps of people that know how to. It's a little puzzle box that you need to solve, and it's I encourage you to try and see how useful it is to see attention maps of people that know how to solve the puzzle box, and hopefully, it will help you to solve it faster than without the augmented reality help. And
Thank you, Alex. So I'm Dulanga. I'm a postdoc at Smart, working on the T1 project. So I'll come to the next part of the research milestones that we have. So we are looking at two different problems again. So one is the 3D spatial awareness, and the other one is instruction grounding. I'll come to why these two problems are important for the use case that we are after in the M3S. So Prof. Jinhu talked about the overall goal of the project is for the humans and the machine to work together. So one key capability that you require in such a case is that you need to localize different objects, different humans, robots, and all that within a shared 3D environment. So how do you do that is using something called the spatial awareness, where we use multiple LiDARs mounted on different areas. So you need to map them together into a single coordinate space. But the problem now is that when you have multiple LiDARs, the LiDARs tend to interfere with each other and causing LiDAR interference. So you won't get the accurate spatial awareness. So how do we mitigate that? We propose a low complexity model for identifying the interference happening, and we have a very shallow network which can actually mitigate the occurrence of such interference. The second problem is again very much related to the problem of humans and machines working together, so which is called natural human instruction grounding. So the key idea is that when robots and machines who are working together, you need to have a mechanism where the humans can give out instructions in natural instructions, gestures, and all that. So there should be mechanisms in the machines to be able to comprehend them. But the challenge is that how do you do them continuously in a resource-constrained devices like smart glasses, mobile devices, and all that. So which is very challenging because you need to do spatial understanding, you need to do temporal understanding, all within a very resource-constrained device. So this is one of the examples. So this is one of the examples that in this case we have a RGB video stream and an instruction where the instruction is identify the girl who's dancing. So you need to figure out spatially the location of the girl and also to temporarily segment when that girl appears in the screen and leaves. So for this particular case, we are using something called an event stream, which is an upcoming sensor similar to RGB, but the only difference is that the events are asynchronous. Whenever there is a brightness change, that particular pixel is asynchronously triggered. So the benefit of using such a sensor is that you can use them for low power sensing because it's asynchronously triggered. You won't have the same overhead like an RGB camera. So what we do is, the key approach that we use is we use the event camera for motion tracking, which we can do with very little processing, but we only invoke the RGB images only on the key semantic changes. So by doing so, we actually achieve 4 times faster and energy efficiency by doing this simple approach. So the next steps, we are looking at 2 different scenarios again. One is the efficient spatial awareness, where we are so the problem is when you have multiple LiDARs, each of those LiDARs will have their own emitter and the receiver. So it consumes a lot of energy. So is there a way to reduce the amount of energy that those LiDARs use? So one way you can do that is we call it decoupling LiDARs. We kind of separate the emitter and the receiver. So there will be only one emitter, multiple receivers mounted. Because you have only one single emitter, the power that is consumed by the whole system will be drastically reduced, and you won't also have the interference problem because there are no multiple emitters working together. So the next problem is again related to the human instruction understanding. So we have talked about a lot about explicit knowledge like verbal instructions, gestures, which has already been done with our previous work. But is there a way to also capture the implicit knowledge to improve the accuracy, like what Alex talked about. So there are certain things where you might be looking at something, but your cognitive attention is somewhere else. Is there a way to reveal those hidden information and use them to improve the accuracy, maybe to reduce the latency, and so on and so forth? So this is our team, and yeah, thank you.